Hello everyone, this will be my presentation on the VLSI Champion course. So through this presentation, I will cover the following topics. So first will be the topics covered in all the classes, followed by a brief overview of each class's topics, then followed by some of the codes that we learned and implemented through Verilog and VHDL, and then finally the final assignment submission. So the topics covered. These are the main topics covered through the course of 10 classes. Now, the overview of topics. In class 1, we started off with an introduction to VLSI and learned how it is the process of creating an IC by combining millions of transistors onto a single chip. We then went on to study the structure of a MOSFET or the metal oxide semiconductor field effect transistor and how it has three terminals: the gate, the drain, and the source. Current flows from the drain to source or the source to drain, and it is a voltage controlled device. The MOSFET structure includes a substrate with N or N plus or P plus wells. We further learned about the depletion type and the enhancement type of MOSFETs. So in the depletion type, if the gate to source voltage is 0, an N channel is still present between the two wells. Electrons in the channel flow towards the drain, therefore the current flows from the drain to source. When the drain to source voltage is increased, the flow of current also increases. If the gate to source voltage is made negative, then electrons are pushed towards holes, and when the electrons and holes combine, the channel length decreases and the current also decreases. There will be a pinch off point that occurs when the current is 0. On the other hand, when the gate to source voltage is positive, electrons in the substrate move towards the channel and the channel length increases, which leads to the current also increasing. In the enhancement type of MOSFET, if the gate to source voltage is 0, then there is no channel present and therefore no current flowing through the MOSFET. If the gate to source voltage is made positive and the drain to source voltage is also positive, electrons move from the substrate to the gate and the channel length increases, therefore the current also increases. There will be a threshold voltage, that is the voltage at which MOSFET turns on. Now, if we keep the gate to source voltage fixed at a point greater than the threshold voltage so that the MOSFET is on, and increase the drain to source voltage, then the drain current increases and saturates at some point. Now we'll have three regions in the enhancement type. That will be the cutoff region, the linear region, and the saturation region. In class 2, we learned the basics of the BJT and how we have an emitter region that is heavily doped, the collector which is lightly doped, and the base which is in between the emitter and the collector in terms of doping. We also learned about the two different types, that is the NPN and the PNP transistors. We then moved on to the basics of the PN junction and how in the P-type region you'll have holes which are the current carriers, and in the N-type region you have the electrons which are the current carriers. Now the N-type electrons will move towards the P-type and vice versa in order to get neutralized. After neutralization, a region is formed which is known as the depletion region that lies in between the P and N types. This was followed by the reversed bias operation. So reverse bias is where you have the negative end of a battery connected to the p-type and the positive end of a battery connected to the n-type. The electrons in the n-type flow towards the p-type and the holes in the p-type flow towards the n-type. Here the depletion region increases, therefore at some point some holes cannot jump into the other regions, and the same goes for the electrons. And so in this case your current keeps decreasing. In the forward bias operation, you'll have the other way around, with the positive end of the battery connected to the p-type and the negative end of the battery connected to the n-type. Here the depletion region will be smaller, and therefore your current will increase and is larger compared to the reverse bias current. Then we moved on to the working of the BJT and the regions of the BJT, that is the cutoff region, the saturation region, and the active region. In the cutoff region, you'll have both junctions, that is the emitter to base junction and the collector to base junction in reverse bias. Therefore, no current flows through the device. It will be in off state and operates like an open switch. In the saturation mode, both your junctions, that is the emitter to base and the collector to base junctions, will be forward bias and the current flows through the device. We also covered the common BJT configurations, which is the common base, common emitter, and the common collector configurations, as well as their related formulae. In class 2, we also covered Moore's law, logic gates, and CMOS. In CMOS, we learned how an NMOS transistor, if the input is 1, then the switch is on. However, for a PMOS transistor, if the output is 0, the switch will be on. So the source of a PMOS will be positive and the source of NMOS will be ground. We also learned how two NMOS will operate in series and parallel, as well as a CMOS circuit for a NOT gate. We finally ended the class with VLSI design styles and how you have user programmable, semi-custom, full custom, and system on chip devices. In class 3, we learned about programmable logic devices. We started off with the ROM, which is the read-only memory and is a fixed memory where we cannot change the values of input and output. We then learned about the PROM, which is the programmable read-only memory, which has a fixed AND array and a programmable OR array. The OR inputs are programmable in this. We can program any number of required product terms, since all the outputs of the AND gates are applied as inputs to each OR gate. PROM will have two basic versions, which are your mask programmable and your field programmable. The mask programmable can be programmed only by the manufacturer and has less delays because they are hardwired. In field programmable, you'll have types like EPROM and E2PROM. They are programmed by the end user. In E2PROM, electrical signals are used to erase the chip. We then learned that the PAL has a programmable AND array and a fixed OR array, while the PLA has a programmable AND as well as a programmable OR. We then moved on to CPLDs, or complex programmable logic devices, which are a semiconductor device containing programmable blocks called macro cells. Now the CPLD architecture will include PLDs, input-output cells, and a programmable channel. So the PLDs will either be a PLA or a PAL, and the connecting channel connects the different PLDs. We then ended the class with an introduction to FPGAs, which are semiconductor devices based around a matrix of configurable logic blocks, or CLBs, connected via programmable interconnects. Now, FPGA, as the name has, field programmable, it means that the user can program this the FPGAs, and it has three main components, which are your CLBs, your programmable interconnects, and your input-output blocks. Now, your CLBs are your basic repeating logic resource of the FPGA. Its routing resources include the interconnects, and the components of the CLB execute complex logic functions, implement memory functions, and synchronize code on the FPGA. The components of the CLB include flip-flops, lookup tables, and a multiplexer. In class 4, we covered some of the main components of the FPGA. We started with the SRAM, or the static RAM. The static RAM, unlike the DRAM, doesn't require you to refresh it in order to add content. Data is held statically, that is, as long as power is applied. And when you put an input on the bit line, the first transistor turns on and then goes through the coupled NOT gate to where it is stored. The bit line is where you input your data, and you have a word line which is 0 when nothing is stored or when you want to write. We then moved on to the LUTs, or the lookup tables, which are analogous to logic functions implemented using a 2 power n to 1 mux. If you have two inputs using an FPGA, you can program the LUT as any gate to operate on the operands A and B. They can also be erased and used as a different gate. It basically consists of memory and a mux. The number of input variables will be the number of LUT inputs. While realizing the function using an FPGA, the value of the output variables for each of the combinations will be stored in the SRAM. This was then followed by the FPGA design flow, which includes your code or schematic, which is then synthesized, then translated, then mapped, then placed and routed, which is then generated into a bit stream, and then finally downloaded. The synthesis process is a process which translates VHDL or Verilog code into a device netlist format, that is, a complete circuit with logical elements for the design. Your implementation consists of 3 steps, that is your translate, mapping, and placing and routing. Now translate combines all the input netlists and constraints to a logic design file. Now defining constraints means we are assigning the paths in the design to the physical elements like pins, switches, etc. of the targeted device and specifying time requirements of the design. This info is stored in a file named UCF, or the user constraints file. In mapping, the NGD file is mapped to obtain an NCD file. In the mapping, static timing analysis is taken place. Finally, the placing and routing step is nothing but placing the paths and making the connections. In class 5, we covered static timing analysis. We first began by learning how in the 70s this was performed with SPICE simulation. In the 80s, timing was included in Verilog simulation to determine if the design was sufficiently fast. But two problems were present with either approach. One is that analysis was only as good as the simulation, and logic simulation were 5 to 10 times slower. In static time analysis, which is more comprehensive, one calculates the time for every component and every path. We then moved on to learning the clock attributes, which are the period, the duty cycle, filter, and phase. Filter is when there should be an input when there is a rise in clock, but if there is a delay, this will be known as your filter. We then learned about static time and hold time. Static time is defined as the minimum amount of time before the clock's active edge that the data must be stabled for it to be latched correctly, while hold time is defined as the minimum amount of time after the clock's active edge during which the data must be stable. We then looked into clock analysis for a D flip-flop. We learned about clock to out, that is TCO, also known as the clock to Q, which is defined as the time delay from the active edge of the flip-flop's clock input to the resulting change in the Q output. We learned how every device path in a design must be analyzed with respect to timing specifications or requirements. Designers must enter timing requirements and exceptions. We learned about the different paths present in an FPGA, for example, register to register, or you have your data path as well as your clock path. We then learned about hold analysis, where we have two things to consider. One is your minimum delay along the data path and your maximum delay along the clock path. If the difference between the data path and the clock path is negative, then there is a timing violation. In hold analysis, to find the delay in a data path, you have to consider only the minimum times. To find the delay in the clock path, you have to consider maximum timings of T clock and T hold. Finally, we calculate the hold slack, which will be your TD minus TCLK. If the hold slack is positive, then there is no hold violation. Setup analysis is in a way opposite to hold analysis. For the delay in data path, you will consider the maximum timings, while in delay in the clock path, you will consider the clock period plus the minimum timings minus the setup time. Finally, you calculate setup slack as TCLK minus TD. And here again, if it is negative, then you have a setup violation. Like I mentioned before, we learned about the kinds of paths, which include your input to register, register to register, and your register to output. In class 6, we covered full custom design, which is a methodology for designing ICs by specifying the layout of each individual transistor and the interconnections between them. CAD tools are used for the same, and they are customized for customers. We then learned about the VLSI cycle, which includes system specification, then functional design, logic design, circuit design, physical design, design verification, fabrication, and finally testing, debugging, and packaging. We learned how system specification is basically where you define how a circuit should be. Functional design includes your netlists and translations. Logic design includes defining your truth table and defining which is your input and which is your output. The circuit design involves the circuit made according to the last three steps, and your physical design is your full custom design made on tools like Cadence, which includes a stick diagram. Physical design, where you're converting your circuit description into a geometric description, which is then going to be used for fabrication of this chip, involves three steps, that is partitioning, floor planning, and placement and routing. So in floor planning, it includes a sort of blueprint where you need to find efficient ways so as to have less delay, and routing is where you essentially make connections. In the first step, partitioning, the following should be kept in mind. The blocks that you make should either have well-defined areas and shapes or have approximated areas and no particular shape. That is your fixed blocks and your flexible blocks. In the floor planning and placement steps, your input to the floor planning is your set of blocks, both fixed and flexibles. Pin locations of the fixed blocks are done here, and the aim is to minimize area in order to make the circuit more efficient. The shapes of the flexible blocks are determined, and with respect to placements, the aim would be to minimize the total length of interconnects, which simultaneously reduces area. You have two types of placement, which is global placement and detailed placement. Global placement is accessible by all paths, while in detailed placement, certain paths only certain other paths can access. Finally, routing with the given placement netlist and tech info, the necessary wiring is determined. We ended the class with a brief of standard cell. Standard cells, also known as semi-custom, have some predefined libraries, and all the commonly used logical cells are developed, characterized, and stored in the standard cell library. Typical libraries contain a few hundred cells, and each cell is defined with a fixed height that cannot be changed. In class 7, we covered layout and stick diagram. So some things that need to be defined by the designer are transistor widths, spacing, interconnect widths, contacts, wells and their contacts, and other sizes. Now, we learned about the feature size, which is the distance between source and a drain, as well as a brief about lambda rules. When it comes to the stick diagram, we learned that when the same types of sticks cross, there is an electric contact. For example, a metal over a metal, an electric contact will be formed. If different sticks are crossed, say a poly over a metal, then no electric contact is formed. And if an electric contact is needed, then a contact needs to be drawn. In the CMOS stick diagram, you will find a demarcation line with PMOS and NMOS on different sides. We further explored various stick diagrams and layouts in this class. In class 8, we covered system on chip, which is an IC that integrates multiple components of a system onto a single chip. We learned that power management is the biggest issue of a system on chip, and it is more of a system and not on a chip, in addition to being an IC. SoC consists of software and interconnection structure for integration and consists of some or all of the following: memory, processor or CPU core, analog circuit, accelerator or application specific hardware modules, and finally software. We then learned that SoC has certain design trade-offs or 5 big issues for SoC design, which includes power consumption, chip area, time, reliability, and configurability. We then covered power dissipation in VLSI. We learned about why it matters. The things involved include costs associated with packaging and coding, standby time and battery life, digital noise immunity, and environmental concerns. We learned that there are two main types of power dissipation: your static power dissipation and your dynamic power dissipation. Static power dissipation occurs in the form of a leakage current when the system is not powered on or in standby mode. Its source include subthreshold leakage, diode around the transistor, or your gate leakage. Dynamic power dissipation occurs due to switching of transistors. We also briefly looked into the solutions to the power dissipation problem. So minimizing power dissipation with low power design can include reducing supply voltage, physical capacitance, and the design process itself. In reducing your supply voltage, 2 reductions can result in a factor of 4 reduction in power consumption, but your performance is also reduced. Now, dynamic power dissipation directly depends on your physical capacitance, while your design process will include reducing feature size, which also will result in a lower device size. In class 9, we continued with topics on SoC and we started with the chip area. We learned that good design does not imply a maximum yield. Reducing area below a certain amount has only a marginal effect on yield, and additionally there is a required area for pins and for separation between adjacent dies on a wafer. We came across an interesting example as to why input-output ports are placed at an edge. For example, on a phone, you have all the connections along the edge. This avoids interconnections as compared to if it had been placed in between. The area available to designer is a function of the manufacturing process technology. This includes the purity of the silicon crystals, the absence of dust and other impurities, and the overall control of the process technology. Other impurities may get added when manufacturing. Improved manufacturing technology allows larger die to be realized with higher yields. We then moved on to cycle time, which relates to performance. So the cycle of a clock is the basic time unit for processing. There will be two types of systems, a synchronous system and an asynchronous system. In a synchronous system, the clock rate is a fixed value and the cycle is determined by finding the maximum time to accomplish a frequent operation in the machine. While in an asynchronous system, time is determined by the completion of an event or an operation. A completion signal is generated that then allows the next operation to begin. We then moved on to reliability, which is related to deep submicron effects. We learned that in order to improve reliability due to a single event, techniques involving voltage scaling and application task mapping can be applied. We also briefly looked over photolithography, etching, and how, because sometimes masking doesn't take place well, task mapping was applied to overcome this. We also went into configurability and how standardization in manufacturing and customization for application, its pros and its cons. We finally ended the class with a look into the inside of SOCs. One component is your CPU. Then it has a GPU, which is responsible for the graphics, which is something not needed for an FPGA. It then has DSP, which has audio processing, video processing, and display, followed by connectivity modules that include cellular radios, Wi-Fi, FM radio, and USB. Memory is a variable in a system. It can either be placed above the processor or a package on package. Finally, in class 10, we learned briefly about a silicon on insulator where your capacitance and performance is increased. Here, it follows a different method of fabrication. A thin layer of silicon is placed on top of an insulator such as silicon oxide, also known as the buried oxide layer. This layer lies upon the substrate and isolates the body from the substrate. The transistor is then built upon this thin silicon layer. Full dielectric isolation of the device decreases parasitic capacitance, therefore improving performance. We looked into the structure as well as the types of SOI, which include partially depleted silicon on insulator and fully depleted silicon on insulator. Section 3 is Verilog and VHDL, which includes all the code that we learned and implemented. We first learned how to implement all the gates in Verilog, the function of the assign keyword, and how to instantiate the modules. We also learned how to implement a test bench of the same. We then checked the working of a half adder using Verilog and implemented the same, followed by the full adder, which we implemented in all different styles of modeling, which includes data flow, behavioral, and structural. We also learned about how to implement gates in VHDL, where you have an entity and you have architecture. Finally, the final section includes the final assignment and its implementation. Starting off with the Verilog implementation of the assignment, the circuit included two inputs, but each had 2 bits, which is why I have assigned input A and B as 1 to 0, and it includes three outputs, out 1, out 2, and out 3. I included an always statement with A and B in its sensitivity list and began it with three if cases. So if if A is lesser than B, then your out is 1, otherwise it is 0. If A is equal to B, then your out 2 is 1, otherwise it's 0. And finally, if A is greater than B, then out 3 is 1 and otherwise 0. This is the final graph that includes the waveform of output 1, 2, and 3 as well as A and B in all case conditions. This includes a video of the simulation. We start with the 0, 0 case A and B where your output 2 was 1, followed by 0, 1, then 0, 2, where always output 1 will be 1 because A is lesser than B. When you have 1 is greater than 0, your output 3 goes to 1. 1 is equal to 1, your output 2 is 1. Again followed by output 1 being 1 since A is lesser than B. Two is greater than 1 and 0, therefore output 3 goes to 1. Finally, in the last case, 3 is greater than all. So output 3 remains 1 except for the last case where 3 is equal to 0 and your output 2 is 1. This includes the truth table I formulated based on all the conditions and all the inputs to A and B. This is the K-map for output 1. So 1 is placed in the required cells of the K-map and you have three sub-equations, some product terms which are then summed to get output 1. This is K-map 2 for output 2. Again, here you will have 4 product terms that are added. Finally, for output 3, yet again you have 3 product terms that are finally added for your output 3. Finally, with that, I conclude my presentation. I would like to thank our teacher, Vaishnavi ma'am, for her time and guidance, as well as my peers for their support.